What happens when a wave encounters a new medium? We saw it a little bit last time, but we need to finish that up. And then we have some more demos today. Some nice demos. All right, first things first. You ready? We've got a wave, a pulse. Okay? Our pulse is coming along, and I have my pulse going to the right with a velocity. It has a certain amplitude.
Yes.
All right? It has an amplitude. When it reaches a boundary, a new medium, okay? If the new medium accepts the energy at the exact same rate as the old medium, it could A be the exact same medium, or it could have maybe the properties work out so that it has the same speed of the wave, right? Okay, that actually gets into quite a bit of complicated physics, but we'll just say if the speed of the wave in the new medium is the same as the old medium, then it accepts the energy at the same rate it's being supplied. Therefore, all of the wave will go straight through to the new medium. All right. This explains why, when I speak, I don't get an echo through the air. Because the air here in front of me and the air in front of you is the same medium. It accepts the energy at the same rate, passes through at the same rate, so it goes straight through to you. Now, my wave that hits the wall in the back of the room, there's an echo from there because the wall accepts the energy at a different rate. It travels through it at a different speed. Therefore, when the wave coming from the air hits the wall, it won't go completely through, and some of it will reflect. Okay? Let's first talk about the wave that transmits into the new medium. Okay? All right, transmission. The transmitted part of the wave. You need to know these things. The part of the wave that goes through will be in phase. Okay? In phase means it has the same characteristic, like if this one's on the top side, this one will be on the top side. It's not flipped over. Okay? And that should make sense. If you shake someone's hand and you're shaking your hand up,
and they're down,
their hand won't go down when you bring your hand up, right? Because this is the driver, this is the receiver, so it's going to receive it into the same direction. Okay? So it's going to be in the same phase. It will not be flipped over. So if this one's upright, that one's upright. If this one's upside down, that one's going to be upside down. Okay? Also, because this is the driver and this is the receiver will receive it at the same frequency that it's been presented to them. So like if I shake my hand up and down once a second, and I grab your hand and shake my hand up and down once a second, then your arm will go up and down once a second. If I go up to the wall and tap on the wall twice a second, it'll send a sound wave through the wall at a frequency of 2 hertz, twice a second, right? In the new medium. Now think about that. You can stick your ear to a door or to a wall and hear the people on the other side, and you can pick out who the people are. Because the frequency of their voice remains the same in the new medium. Right?
Yeah, because each thing will hit it.
Yeah, because like if I speak with my voice a certain frequency, it's going to hit the wall. A lot of my wave's going to reflect back, but some will go into the wall, and the wall will vibrate with the same frequency that I'm speaking in air. And then when it goes through the wall and goes to the other air out on the other side, it's going to go back to the. It's going to go. It's still going to have the same frequency. And even if you put your ear up to the wall, you're going to be able to hear that voice. And it's the same pitch, same frequency. All right? So the transmitted wave is in phase and has the same frequency. That's important. All right? Now, its amplitude may be less. If the amplitude over here is less, then what does that mean? Yeah, either that some of it's lost. Now, we're going to be in our imaginary physics world where the energy's not just goes away. Now, like in sound deadening materials, what happens is the material turns the sound wave into heat, usually. So what happens is the sound wave goes in, oscillates the material, and the material warms up, but the sound wave dies. So, if 100% of the wave comes towards this new medium, and only 70% goes through in the same direction, then what happens to the rest? Assuming it doesn't all just get absorbed, it's going to have to be reflected off. Okay, so let's talk about the reflected part of the wave. You have two options for what the reflected is going to be like. Number one, I forgot one thing. The transmitted part of the wave. It has the same frequency. Will it necessarily have the same velocity? No. In fact, if they don't have the same, if 100% doesn't go through, they won't have the same velocity, right? So, frequency is the same. Velocity will probably change. So if the velocity goes up in the new medium, then what would happen? Very good. Velocity equals frequency times wavelength. If this stays the same and this goes up, then the wavelength goes up. If the velocity goes down, then the wavelength goes down, but the frequency stays the same in the new medium. All right? All right. Forgot about that. All right, now let's talk about the reflected part of the wave. Okay, since this is a different velocity than this one, some of it's going to be reflected. How will it be reflected? Well, you have two options. Option number one, it will reflect like this. Option number two, it will reflect like that. Upright, which doesn't mean necessarily pointing up, it just means on the same side. So not inverted or upright, or inverted. Okay? Which one do you get? Well, it depends on the difference between the two medium. Okay? If this medium is more dense than this medium, then it will get flipped over. Okay? So if you go from less to more dense, it'll get flipped over. Inverted. If you go from more to less dense, then it will just go in and bounce right back upright. Okay? Alright, so let's talk for a minute. I'm making my sound wave right here. My sound wave goes up and hits the wall. Would you expect more transmission of the energy through the wall, or would you expect more reflection of the sound energy? Why? Because there's a vast difference between air and cinder block, right? The more the difference between the two, the more reflection you're going to get. The more similar the two, the less reflection you're going to get. Okay? Alright, so here we go. Reflection. More reflection if they're dissimilar. More transmission if they're similar. Upright and inverted reflections. Got it? Hey, quick question. What's the frequency like of the reflected wave compared to the transmitted wave?
Same.
Why?
Because you're still hitting it at the same rate.
I got an even easier one. It's in the same medium, right?
So frequency will always remain the same?
So frequency here and frequency here is the same. The velocity here and the velocity here is the same. And the wavelength here and the wavelength here are the same because it's in the same medium. It just reflects back into the same medium. Over here, the frequency stays the same, but these two will change. Okay? Alright, so we got that going for us. Now, let's talk about when waves meet. Okay, when waves meet, we have what's called superposition. Or interference. Interference. Right. Okay, interference. Okay, we talked about this a little bit last time. If a wave like this meets a wave like this, and they're coming at each other like this, when they meet, we're losing some here. When we meet and they overlap right in the center, then if this is an amplitude of A and this is an amplitude of A, then this would be 2A when they meet. And then they pass right through each other. Eventually, they'll go by each other and they'll just keep going. All right? This is called constructive interference. And the superposition thing means is that all you have to do is superimpose them on top of each other and add them up. And that's what the new shape will be. All right? So if you happen to be standing here and this was sound waves, what would it sound like? Loud. Right? This would be loud. If these are two ocean waves and you're right here, then yeah, it's a you get I better hold your breath. That's right. Okay? If these are two light waves, then this is brightness. Right? This works for any kind of wave. Okay, so what if you have a wave like this and a wave like this that meet? Okay, when they meet right in the center, they will cancel each other out and you'll have what's called destructive interference. So constructive or destructive interference. But here's the thing. This destruction is only of the motion, not the energy. The energy is still there. You just don't experience it. And then it'll pass right through each other. So it doesn't like make them, oops, I made it the wrong way. It's not like it makes the waves go away permanently. It's just when they meet. Okay, so they'll go past each other. But if you're right here and these are two sound waves, what do you hear? Nothing. If these are two light waves, what do you see? Nothing. Darkness. These are two water waves.
Water. Negative light.
You experience nothing.
Don't have negative.
Okay, how many of you gone to Hurricane Harbor or a wave pool?
That one specifically.
Okay, you been to the wave pool? Okay, you get in the big wave pool, and there are certain regions where it's fun and not so fun. Fun or boring. The fun spot is where the waves meet crest, or trough, and you get big waves building up, right? They go up and down real big. And then there's the regions in the pool that you get tired of this because you're getting beat up, right? And so you swim to this region where the waves are still there, but what's happening is they're meeting crest trough, and they're kind of canceling out. And so you're not really doing much. You're just kind of floating there, right? All right? You see all the people congregate in these areas, right? In the wave pool, what you see is it looks like this. And the wave pool goes out, and there will be a region down the center, and there'll be a region here and a region here usually where the big waves are. And then in the middle here is where, you get tired, that's where you swim to, so you don't drown, right? But here's where all the kids are congregating. There's a bunch here, there's a bunch here, and a bunch here, and a bunch here, where the waves are actually hitting and cresting and going over, right? All right. That's called constructive and destructive interference, and you find the shape by just superimposing them and adding them up. Okay, on the test, somewhere, you'll be asked a question. Okay, about this. On the test, that's correct.
They're going to ask us questions.
They will ask you a
I
question.
don't like questions. I prefer tests without any questions.
I know, life's tough because you have questions. And they'll ask you a question like this. Alright, these two waves are traveling at each other. Alright? When they meet, yes, when they meet, which of these things might you see? Could you see A? Could you see B?
Well, when they meet at the center?
Could you see C?
Mr. Brown, on the homework to do this question, I had to cut the paper out and put it on top of each other.
That's okay. It's all right. Could you see D? Where that's 2A. Could you see E?
What did you just thought?
Yeah.
Could you see F?
Did he specify where they would go?
No.
He said,
What they traveling?
Yeah. And then it's just gotta be like a A, C, and E thing, or a B.
Could
D,
you see G?
You can stop now. The alphabet goes to Z.
Could you see H?
You should make one with a Z.
Could you see I?
Wow.
Could you
So is this
see
our only question
J?
on the
Are you gonna
test?
do all 26 options here?
Then he's going to go on.
All right,
another
which of
alphabet.
these will you see when they meet and cross through each other?
Cross the field.
After they cross through? Like,
Anytime, which of these could you see at any time? As they're approaching and passing through each other.
You can see D for sure.
Okay, when will you see D?
Whenever they're like the left part.
Whenever this one is like right here,
Yeah.
So C.
And then
okay? Circle C,
then you can
You
see
can
D.
E.
When those two just meet,
You can take E.
the one
Okay,
that's.
when would we see E? Make that in blue.
The two parts closest to each other
When-
meet.
Oh, when it's like, when this one is right here.
Yeah.
Yeah.
And they cancel.
Okay, because this will be added to nothing, so it'll look like that. The blue up and the black down cancel, and then the blue down adds to 0, so it looks like that, right? Very good, so that's what you'd see. Any others that you could see?
No.
A? No, wait.
Just one. Just if you split it.
G.
Yeah.
No, you went to G. The last part has to be at the very bottom. For you to see G.
I like H because I don't know where it comes from.
F is almost correct.
Yeah.
If,
That was at 0.
if you would do this and take this one and place it right here,
When the two first ones
Yeah.
then it would look like this, up, down, and then up, but this should be down, right?
Yeah.
So if it was like that, then F would be one of our options, right? Okay. They're going to ask you something on the test. They're going to say, okay, you got a wave like this, and it's going to be approaching a wave that looks like this. What are your options for when they meet? Okay? And they'll give you some options. You just pick out the right one. There'll only be one right answer, probably, on the AP test. They probably won't have a multiple one like we have here.
Yeah, with a Scantron up to J.
Yeah, Scantron up to J.
And it has to be 2A. And negative C.
I'm guessing would be.
That's true.
All right, let me see if we can experience this. Do you hear that?
Yeah.
The difference.
Yeah, the bounce.
That wobble in the amplitude of the sound? Wow, 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 wow. Right? Okay, now listen. Speeding it up?
No, you can hear different.
Oh, yes, and you'll hear it different in different ears, too, because it's going to pass through your head.
It passes through some people's heads and others.
Okay. You hear? It's almost the same now, right? Okay, what's happening is I'm playing.
This is the Star Supreme.
Is it just?
Just at a different frequency.
All right, what I'm doing is I'm playing two notes that are almost the same. They're off by a little bit. Okay? Now, if the two notes are exactly the same, then they'll have a tendency to travel together and add up, right? But what I'm doing is I'm adding two notes that are slightly different. I have a note that looks like this, and hopefully I can do this right the first time.
Nice.
Yeah, but I got to do this one slightly different. All right, I have two notes. I'm going to add them up. So what happens is, notice that these two meet crest, right? And right here, they're crest, trough, and then they're crest, and then they're crest, trough, and then they're crest again, right? When they meet crest, what does it do? It adds up, and you get constructive interference. When they meet crest, trough, what are they like? Okay, they have destructive interference, right? Not deconstructive interference. So what you end up with is a wave that'll look like this. It'll be high amplitude, down to no amplitude, and then up to high amplitude, and then down to no amplitude, and then up to high amplitude, and then down to no amplitude again. And what you end up is when you add these two together, you get something that looks like this. Now, what the heck is that? That is high, low, high, low, high, low, big, soft, big sound, soft sound, big sound. You're getting loudness, softness, loudness, softness, loudness, softness. Now, how many of you play a musical instrument? Anybody in band? Okay, band members are trained to listen for this and to hate it. Because when you hear that, what does that mean? That means that your musical instrument is out of tune. Somebody
else playing off.
Yeah, somebody else, not you, of course. That's right. It means that you're playing two notes that are not exactly the same. How do you get rid of it?
Or making
Yeah, you tune your instrument until everybody plays the same note. If you've ever been to a concert or orchestra or something, they will play their instruments. Yeah, and what they're doing, like an orchestra, it sounds really crazy because everybody starts playing this note, and you're like, what are they doing? It sounds horrible. And all they're doing is trying to all play the same note, and they listen and they hear, do I hear that wobble? If I hear that wobble, I'm out of tune, and then so I need to readjust my instrument until everybody plays the same note. So that's how they get themselves in tune. This right here is called the beat frequency because the sound wave beats high, low, okay? So let me write that down. This is called beat frequency. Beat frequency. And the way you find beat frequency, which is usually called F sub beat, that is frequency 1 minus frequency 2, and you take the absolute value. Okay? That's easy enough. All right? So, let's do that real quick over here. Okay, now listen. This is 199 hertz. This one I don't really know because it doesn't have a digital output. It's around 200, but let's see. Listen to the beat. Is that about 1 a second? Roughly?
It's faster.
A little faster than 1 a second? So this one says 199. That means this one could be what?
198 or 200.
It could be 198 if I'm off. If I hear this wobble once a second. Or it could be 200 or 198. Now I'm going to try 198 first.
Oh, there you go.
Does that sound good? So it seems like I'm in tune. So this must be playing around 198. Let me try it to 200 and see what happens. You hear how it's gotten worse?
Yeah.
Okay, so that's the wrong way. And that's how you can tune your instrument. All right? They actually have electronic devices that help you do this nowadays to tune your instruments if you want. But like if you're in orchestra, what you'll play is what's concert A, I think, is 440 hertz. And that's usually the note that everybody tunes to, if I remember correctly. Okay? All right, now let me show you a different interference pattern. Okay? I'm going to hook up the... Now, I'm playing a single note, around 400 hertz note. They are both outputting sound. But one is outputting sound here, and one is outputting sound here. So I'm getting a three-dimensional wave going out here, and a three-dimensional wave going out here. Now, the thing is that when this one puts out a crest, this one puts out a crest, but the crests are being made in different spots in space. When they meet each other, crest, crest, you'll hear a loud spot. When they meet each other, trough, trough, they make a loud spot. When they meet crest, trough, it should make a silent spot. Now, we're in a room that has lots of reflections of sound. So we won't have a completely, totally perfect destructive interference spot. However, you should be able to walk through the room and find spots where it's louder and softer. Okay? All right, ready? Are you ready to do that? All right, everybody get up. Walk around the room. See if you can find spots with loudness and softness.
Loud spot.
Hey, by the way, it's three-dimensional as well, so.
It's loudest straight here.
It's getting loud.
It's quieter out there. It's loudest when you're at the height of the speakers. It's loudest at the height of the speakers.
Yeah. If you walk straight down the center, you should have loud spots all the way straight down. Well, if you're right here, oh man, it's loud. All right, if you stick your head at the level of the speakers, there should be a loud spot right here, all the way out.
Oh yeah, there is.
Now you're good.
Oh yeah, you can.
It's all right here.
Yeah, but like right at this level,
Oh, yeah.
it should be really loud. All right. Yeah, let's turn that down so we don't get headaches. All right. Everybody have a seat. Now, everybody, those loud and soft spots, when we had the beat frequency thing going, some of you were wagging your head back and forth because it felt like the sound was going through your head. The reason why is because those interference locations were literally transporting through the room. And so like a loud spot, a constructive interference spot would literally move from here to here. And so you'd hear it loud here, and then it would fade out and get loud over here and then fade out. So what you ended up with is it really did feel like the sound was moving through your head. It's really pretty sweet. All right, so let's see here. All right, got that. All right, excellent. All right.
Went over the whole thing already?
No. Well, I'm on track. Let me show you what we just had with speakers. You got a speaker here. You got a speaker here. Now, we will talk more about this next class period. But I just want to give you an intro to it. You're going to get wave here, 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 going out. And from this one, you're going to get a wave here, 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 and here going out. Now I want you to notice. Ooh, I need a red marker. Don't have red. Okay, we'll use green. I want you to notice, everybody, look. Do you see that they meet crest, crest, here, here, here? There's a line right down the middle where they always meet crest, crest.
Silent zone?
No, that's the loud zone where they will meet crest, crest. You have constructive interference right down the line of symmetry.
And there should be even.
I know, I lucked out because usually it's all over the place. Notice there's going to be another one here, 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 and should be out here. It's going to go like this. And you're going to get these lines of constructive interference. Those are the loud spots. Now look, so if you walk through the room, loud, soft, loud, soft, loud, soft, loud, soft. There's going to be this pattern. Okay? Hey, what if we did this with light instead?
Right.
It would be bright, dark, bright, dark, bright, dark. What if you did this with water waves instead?
Like
Wave pool. This is the wave pool. This is exactly what they do. Down underneath that back wall, they have a wave generator that generates two big waves. And the two big waves that come out will cause right down the center a huge wave. And then there'll be another one coming off this way and this way. That's why the wave pools are built in this shape. Right? So they take advantage of those waves as they go out and form those crests, or constructive and destructive interference. Okay, this is going to be true in any type of wave. Water wave, sound wave, light wave, whatever wave. Okay? Alright. Now, just as a crazy side note, to get you ready for modern physics, light behaves like waves, but so does matter when you get down to really small. Protons, electrons, atoms, neutrons, all these things have wave properties. Okay? And when you have these wave properties for matter, matter can also exhibit this constructive and destructive interference, since it has wave properties. And so you'll have really strange things when you get down really small. So what would this mean for matter? When you have constructive interference for matter, that means that the matter exists here, but not here. And it exists here, but not here.
So apple and no apple.
Have you ever wondered from chemistry? You're in chemistry and you got your atom down here, and then it's like you got these weird electron shell things, right? Where the electrons are. Like what? The S shell looks like sphere. You got a spherical shell here and you got a spherical shell here, right? So why does the electron exist here and here, but not here? Because they behave like waves, and you have constructive interference here, but destructive interference here. So they can only exist in the places of constructive interference. The same thing is true of the different shell shapes. Like, what's the next one? What's the one with the lobe? Is that
S is the first one.
S?
S-E-T-F.
Is P like this?
Yeah.
Okay, the P one has these lobes like this, and that's to do with constructive interference as well. Craziness. Okay? So, just as a side note, what we're learning for waves now applies to modern physics and how matter exists some places but not others. Really crazy. Alright. Now, but wait, there's more. What we just did with the sound wave was a two-dimensional interference pattern. Okay? Let's do a one-dimensional interference pattern and make life simple at first. Alright? You ready?
Let's go get Michael.
Hey! Oh! Hey!
Oh, that is beast.
Oh, so it's the high, and then you
This is like ultimate limbo.
That is like awesome. No joke. Can you make it bigger?
What if I touch it?
Yeah, just leave it.
Go ahead, I dare you. Don't touch it!
Wait, am I touching it?
Touch it with your finger.
Use your finger. Just like,
Okay. Now, everybody, see this spot right here? What we have is waves going down to the doorknob and coming all the way back. And when the waves go down and come back, they're going to hit that doorknob. The doorknob is a new medium. The new medium is more rigid. So the waves that go out like this come back upside down. Okay? So what I have is waves going that way and this way at the same time. But it looks like the wave is standing still and just flopping back and forth, right? This is called a standing wave. You get a standing wave whenever you're at what's called resonance. Right? This is resonance.
it's like hardly vibration when you get to that.
Yes. So this is a spot of what kind of interference?
Destructive.
Destructive. This is a spot of?
Constructive.
Okay. This is called, given a name. This is called a node. All right? A node here
And
and an antinode. The opposite of a node is a not a node, an antinode. Okay? Antinodes are spots of constructive. Nodes are spots of destructive. Okay, count them up. How many do we have? One? No, wait a minute. Hang on. First, see where does my wave? Is this one wave from here to here?
No,
Okay, wave is crest and then trough, right? So each one of these loops, sometimes they call them loops, is a half a wave.
4.5.
Okay, so how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9.
4.5.
All right, everybody.
Make it 10.
I'm at. Well, hang on. Let me see. I'm gonna dial it in. Wrong way.
Make them huge. Make them like smack the table.
In the end, it was you.
That wouldn't be very nice way.
You're greedy.
It was nice.
Oh, we're getting smaller. Okay, so right there.
I like
Right there is almost 40 hertz exactly. Okay, somebody tell me, what's 40 divided by 9?
Number.
Quick,
Less than 5.
calculator. 4.444. Okay, let's try it. If I put this down to 4.444, wow, let's see it.
Thank you,
4.444. Hey, look. How many do I have now?
I'm ready to jump rope.
1. Yeah, it's like jump rope. Sit down, you knucklehead. All right, we have 1.
Make it 2.
Okay, if I want 2, what would I need?
Double it.
Double it. So that'd be 8.88.
Actually, the last 8 would round up to a 9.
No, right here on this one.
Oh,
Okay, you see, I have an entire wave now, right? This is one complete wave. Hey, if you have a problem like this, look. Rudy, sit down. This is 8. The frequency is like, say, 8.9. Frequency of 8.9. And how many waves is that? 1 entire wave. If you measure from here down to there, that would be your wavelength, right? Very good. Then I'll give you the velocity. Okay, everybody. Meter sticks. Come on, give me some meter sticks. Line them all up.
Wait, one wave is one standing?
Limbo.
It's two standing
It
waves,
has to
right?
contain
To
Yes.
go like this.
One wave is 2 of these.
So you have to have
things.
3 nodes and 2 antinodes?
That's correct. All right.
You should also get scratch. So you can do this. But it has to be a
All
little
right. Give me this.
Facebook. You said Scrabble is
Here.
the worst.
Somebody help out.
Try to make
We're trying to figure out how long this wave is.
I don't know, maybe it's
It was like 1,000 and
Like,
it
come on,
comes
like,
like Scotland doesn't even know 1,000.
no, now it's Steel wheel.
Here we go. We're just going to line them up.
Come on.
Yeah, you should. So we can make people Scrabble.
All right. That's pretty close. We're just getting an estimate. All right. So is that a complete one?
I know.
So 1, 2, 3, 4, 5, 6, 7, 8. Just say roughly 8. All right. So this wave is approximately 8 meters long. All right. 8 meters long, and its frequency is 8.9 hertz. What's the speed of the wave in this string?
6.2 maybe.
And that's about 8 meters.
Wait.
So the velocity of the wave is
71.2.
Actually, that makes sense.
okay. So the speed of that wave is approximately 71 meters per second.
That's big.
All right.
Is it?
All right. Got it?
Yeah.
I got an equation here somewhere for the frequency of a wave. But let's do this because this is really cool. All right, let's get this to what, 8.8? How many of these do we want? About 5? All right. Give me 4.44 times 5. 22.
How?
Oh, yeah.
1, 2, 3.
All right, looks good. All right. Oh, not collecting.
Wait, Senior Bruin.
Yes.
Why did you say we had 4.444? What's that number again?
We got 4.444 because we had, I don't remember what our original frequency was, and it was divided by 9. However many of these loops we have, you divide it, and that will tell you your harmonic.
Can we turn off the lights? Like the reflection?
All right, I need somebody to turn off the lights and close that door.
Hey, Marco, can I do something? Oh,
Whoa!
This is reminds me of
wait, that's a ceiling fan.
It's the fan! It's the fan all over again.
Changing it. This is called the strobe effect.
Oh my gosh. Oh my gosh. How did you answer this question
Mr.
that I
Bruin,
had 2 nights ago?
Mr. Bruin, we had a physics party.
Hey, look at this. Now watch. I'm touching you. We've done this.
That is.
We did this.
I'm so fascinated.
Isn't that weird?
No, let me touch it. Touch it. And
Now,
then it went back.
why does this work? It's called the strobe effect. Because what's happening,
You only see, the light is only on when it's at that position.
yeah, the light is only on when it's at that position. See, like, look, the strobe effect. Look. Take all kinds of fingers. All right, now, what if I increase the speed?
Oh my god, you have 3 of them.
And does this remind
What is it called? Hopscotch.
Yeah.
Hopscotch.
Wait, look at the hair. It's
Yeah, look.
You're so strange. Mr. Bruin, we had a party and we had a strobe light and we turned off the lights and the ceiling fan, it looked like it was going slow.
Yeah, going slower.
We did the
You can back it
exact
up.
same
Looked like it
thing.
is.
And then you touch it and it's like, all right, sit down up front so everybody can see, okay?
But I mean,
What a strobe light does
That's me in
is it
church.
just
Sit down in their
flash,
case and so
turn
you
off,
can
flash
watch
off, flash off. So you're only seeing it when you get the flash. Okay. Just as a side note, real quick, this rarely, if ever, shows up on the exam, but just in case, the frequency. N over 2L square root tension over M over L.
That would have been very helpful for us.
Yeah, for your lab, did you just do a lab like this?
Yeah, we did, and then I did not know.
We did?
Wow. Remember how I described everything?
All right.
Wait, what's M over L?
Okay, quiet. Come on. All right. T is the tension in the string, or I've written tension. T equals tension. The reason why I wrote tension out in the equation is because T, capital T, looks like time period, which really messes us up. Okay, M over L. What would M over L be for a string?
Mass over length.
Mass per unit length. So that'll be in kilograms per meters. Tension is in newtons. Okay?
Is that equal to velocity or something?
All right, there's a velocity. Well, where's my velocity equation? I wrote down the frequency one. I never remember this equation because I.
tension over
Oh wait, and N.
Yeah, because I use this one so rarely.
Did you say N is? N is the number of repetitions or
force over the.
Oh, here it is. Here it is. This is the one that you used in your lab. Okay, N is the number of loops or antinodes.
Antinodes?
So like for instance, if you have a wave that looks like this, then that would be N equals 3. Okay? Okay, L of course is the length of the string in meters. Okay, what would N be? Oh, I already said it. What's N? It's right there. Okay, so the frequency, if you want to know the frequency of the third number of loops, the third harmonic, then you put 3 in here and you plug in everything else and tell you what the frequency is. All right, one that does show up occasionally, you needed that for your lab, but the one that does show up occasionally is this one. Velocity of a wave in a string is equal to the square root of the tension over the mass per unit length. Okay? That's the velocity of the wave. So what kind of...
So it's just after that one?
Yeah.
So it's equal to n over 2l times.
Yeah, and why does this work? Because look at this. Velocity equals frequency times wavelength, right? And the wavelength is how many of the loops? 2 of them, right? And so if you take that and plug it in here, and the wavelength, you replace it with length times the number of loops, this is really how many wavelengths you have, right? That's how many wavelengths you have. So,
The number of wavelengths or the wavelength?
number of wavelengths that you have in that string. Okay? So it's just velocity equals frequency times wavelength is what that is. All right? Okay. Let's say you play guitar. Okay? The guitar has several strings. Okay?
That's the violin.
That's a bass.
Okay? It's a violin. Because I don't want to draw anymore.
You
Okay?
wanted to go all the way to
One of them's going to be thicker. Let's say that you're at your beginning violin. There you go. It's your beginning violin. It has 2 strings. That string and that string. Okay, which one plays the lower note?
The thicker one.
That one plays the lower note. Lower note means what for frequency? Lower frequency. Okay? Lower frequency. Why would that be? Because velocity equals frequency times wavelength, right? And the frequency, the velocity is given by this. Tension over mass per unit length, square root, frequency times wavelength. Now remember, your strings are a certain length on your device, right? So this is going to be the same in each case. So if I want a lower frequency, what could I do? I could increase the mass per unit length of the string. So the thicker the string is, the lower the frequency, right? What else could I do to lower the frequency?
The tension.
I could lower the tension, right? Yeah, so loosen the string up, right? All right. So on a guitar or any kind of stringed instrument, they will have different mass per unit lengths, different thicknesses per unit length to kind of go from bass all the way up to treble, right? And then to tune them more precisely, they'll change the tension in them to get them to the precise frequency they want. So this gets them in the ballpark. That's the precision tune on a string instrument. All right? Because on a guitar, all the strings are the same length, right? Well, almost. They're a little bit different at the end. Why is a guitar yay big, but a bass guitar is yay big?
Longer.
Because you have a longer wavelength. If you have the same velocity in the same strings, longer wavelength means lower frequency, right? Okay. So like in a piano, like a baby grand or a grand piano, it looks like this. All the keys are here, and it looks like this. All the high-pitched ones are over here, and they're short. All the low-pitched ones are over here, and they're longer. All right? That's why it says shape. Okay?
Not what I was referring to.
Same with a harp. Harp's the same way. It's got a short end and a big end, right?
That's right.
Waves in strings. Okay, you ready? When you have a wave in a string, the string is fixed at both ends. Fixed and fixed. If it's fixed at both ends, then you're going to have a node and a node at both ends. In the middle is where you'll have your antinodes. Okay, this is n equals 1, otherwise known as the first harmonic. The lowest harmonic is the lowest note, the lowest frequency. Okay? Now, velocity equals frequency times wavelength. The velocity will be the same. The velocity will be the same for each of these waves, no matter what the frequency is. Okay? No matter what I do here, that's going to stay the same because it's the same string, right? Okay, so this is our first harmonic. It will have a certain frequency. So here's frequency. This is what's called the N number. And this is our, I'll call frequency naught, and this is called the harmonic. Okay? Sometimes the first harmonic is also called the fundamental frequency. There's a lot of terms to digest here. That's why you need to pay attention, okay? All right, the wavelength here. What's the wavelength of this thing? Now, from here to here, if that's the length of the string, yeah, it's going to be twice as big as the length of the string, right? So it's going to be 2L. It's going to be 2L. All right? All right, now let's go to our next one. Our next one's going to look like this. That's our N equals 2, otherwise known as the second harmonic. Okay? Now let's look at our frequency. I'm sorry, let's look at our wavelength first. What's the wavelength of this one? L. So the wavelength now is L. All right, now look what happened. Our original wavelength was 2L. Our new wavelength is only L. So that's been cut in half. So what has to happen to our frequency?
Double.
Has to double. So this is twice the original frequency. Does that make sense? All right, now let's go to our next one. Our next one will have 3 of these antinodes or loops. So 3 of these. So 1, 2, 3. It's the third harmonic. The third harmonic, what's its length going to be?
2/3 L.
2/3 L. Okay? Hey, so what's happened to my wavelength? From here to here, it's been cut in thirds, right? Because technically, this is 2 divided by 2. This was 2 divided by 1. This is now 2 divided by 3, right? So my wavelength has been cut in thirds. So what happens to my frequency?
Increased.
It's increased. It's now 3 times the original. Do you see the pattern? Okay, that pattern will repeat infinitum. All right? Now, if you play a guitar and you pluck the string, or you play violin or anything else, this is the note with the largest amplitude. Do you notice how when we went to lower amplitudes on that string over there against the wall, that it was bigger, right?
Yeah.
That means it will be the loudest note. So this is the fundamental frequency. The frequency you hear is the note. But this other stuff is also being played, which adds to the texture of the note. Now, if you're familiar with guitar playing, they can play the guitar and then they can touch the string at a certain spot and all of a sudden they'll go to a higher frequency. What happens is if I pluck the guitar string and it's going to oscillate like this and like this and like this all at the same time. But if I touch the string right in the middle, notice that I'm going to destroy this wave, right? Because I'm going to touch it at the antinode and it's going to go away. I'm going to force a node to be right here. If I force a node to be right here, yeah, this one goes away. This one doesn't care. It's going to still play that note. If I touch this one, that one goes away. So what? If I touch it right in the middle, I destroy all the odd harmonics. They all go away. And I'm left with 2, 4, 6, and 8. And so you'll hear the second harmonic instead of the first harmonic. Okay? Okay, let me show you that in a vibrating bar.
Please no.
Okay, now this one. That's annoying. Now this one. Where's the node? Right there. Where are the antinodes?
half.
Now wait a minute. If I go from
Those
if I go from antinode, because they're free to vibrate, right? The ends are free to flex, but the center cannot, right? So if I do this, then there's a node, antinode, antinode.
So it's exactly
So how much of a wave is that?
half.
That's
No, it's 1/4.
it's a quarter of a wave here and a quarter of a wave here, right? So it's a half a wave, right?
Yeah.
Okay. Now, what if I hold it at a different spot? Now listen to this. Listen to this note. Hear that note?
Yes.
Okay, let me try to write at a quarter, somewhere here. If I hold it at a quarter, does that look right?
Yeah, about
About right?
a little bit higher.
Yeah, a little bit
It's a little
lower.
bit higher.
Yeah, it's in a little bit
Lower.
Yeah,
About there? Higher.
Oh, okay, I see the little line now. Okay, yeah, it was that.
Yeah, yeah. It's there.
He's right higher.
Well, that's because he moved it down.
Yeah, haters. That's his haters.
All right,
Don't hit that.
there's about a quarter. All right, now where will the node be now? Wait a minute, so that's a quarter wave here now, right? Quarter, 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 quarter. So now this is one wavelength, right?
Should be.
So I've gone from it being half a wavelength to a wavelength. I've gone from it being like this to this, right? So the frequency should
Double.
double. See if I can get it to double.
This gonna sound terrible. The way you rub it together sounds terrible.
There it is. Ah. Oh, no, I'm not. Oh, and I just threw this down. What the heck was I thinking? Is that a quarter? All right.
We have
Hopefully.
meter sticks, just saying.
No, meter sticks. Psh, meter sticks. I'm off.
The rubbing of your fingers sounds worse than that.
Oh, be quiet. Do you hear the high pitch?
Try
I'm
the other
off.
side.
Meter stick.
Can I try it?
Oh, what was
Good
that?
idea.
What did I hear?
You heard nothing.
Chris was right.
Right here.
He probably kept it right.
There it is.
Oh.
You hear it?
Sound like you're drawing.
Now, why is it a lower pitch? I mean, why is it softer? Because remember, as you go towards more and more
Higher frequency.
higher frequency, they get smaller and smaller, right? Okay. But see, that's a higher pitch than that one, right?
Yeah.
God.
Stop it.
Is that the highest you can make? Because it's fairly simple.
Yeah, because it's exactly half.
What?
You heard biscuit?
The gerbil freaks out.
Really?
Yeah, like he runs.
We gotta watch it, man.
Excellent. Quarterly ears.
Yeah, bad call. Why did
Hear
you do
the.
that?
Oh, wasn't you? I just saw this white man and...
Oh, he is hiding.
Oh, stop it.
Okay. So there you go. That's strings. You ready?
Yeah.
What if we have a sound tube? An open, pipe. Okay? Now, this is a sound tube for sound to go through. Like this thing or this thing. All right? Let me see if this will work.
Sounds like a.
I think it's like.
It was beautiful.
Hey, why does it only play certain notes?
I didn't even
Because it's certain wavelengths.
Because it only the ones that resonate within the tube do you hear. So, look everybody, this is open end and open end. It's free to move. These are free. So therefore you get Antinodes. Just like that singing rod that I was playing around with, right? Okay, everybody.
Vibrated within the room.
How much of a wave is that?
One.
Half a wave. So if this is L, how long is the wave? 2. Hey, just like this. Hey, look at this next one.
Oh, Mr. Hurst made a new posse.
Oh, yeah.
Hang on.
Physics posse.
Hang on. Shh, shh, shh. We got to finish this. If this is L, how long is this wavelength?
3L.
Okay, now remember, this is a quarter of a wavelength, right? Quarter wavelength, 1/4 wavelength, right? So this is one whole wavelength, right? Hey, so look at that. It's one whole length. So the frequency should be
2 times as much.
2 times as much. Hey, let's go to the third harmonic. Okay, how many wavelengths is that? Let's see, I got a quarter, a quarter, a quarter, a quarter, a quarter, and a quarter. Or you could say a quarter, a half, and a half, or that's 1
And then 4.
and 2 quarters, which is 1 1/2.
I would just say
Right? So this length equals 3/2 of a wavelength, right? Just like over here, this length equals 3/2 of a wavelength, right? Or you could say that the wavelength is 3/2 of L, right? I'm sorry, 2/3. Sorry. 2/3 of L, right?
Yeah.
All right. Notice a pipe, like this pipe, only plays certain notes. And it plays the first harmonic, second, third, fourth, and fifth. Come in. I like the little one. All right. This is the exact same behavior as a string, right? So if you know the string, you know this one. Nice. Okay, but wait. They've got to make it more challenging than that. What if you have an closed pipe?
Can we make it close?
If you make it, you could make it closed, but you couldn't hear it really because it's enclosed.
Not only that, but how do you put it?
All right, if it's a closed pipe, it gets a little more challenging. All right? Here's my first one. What do I have to have here at the fixed end?
No.
A node. What do I have to have here?
Open. Antinode.
Antinode at the open end. Oops, open. So I'm going to have a quarter of a wave. That's 1/4 of a wave. So here you go. The first harmonic, n equals 1. All right? N number. My frequency will be frequency naught, and my wavelength is 4 times L. All right? 4 times L. Okay, let's go to our next one. All right, I have to have an antinode here, and I have to have a node here. Okay, if I'm going to start here with a node again, it's going to go like this, back to a node, and then go to another antinode. So it's going to look like this. Now, how much of a wave is that?
Half? No.
That's 1/2 of a wavelength, and that's 1/4 of a wavelength. So if this is the length equals 3/4 of a wave, or the wave is equal to 4/3 L. Ooh, look what just happened. That's 4L over 3. Now wait a minute.
No, wait.
Everybody catch that? This length is equal to 3/4 of a wavelength. So therefore the wavelength is 4L over 3. Did you see we just stopped? We just blew right past dividing by 2, right?
Yeah.
Ooh, this is n equals 3. And this is 3 times the original frequency. A closed open pipe, because the two sides are not equal, only play odd harmonics. Only odd harmonics. Okay? The next one we'll see will look like this. I'm going to extend it a little bit so it'll work. Like this. So look, I have now 1 wave and a quarter. Or length equals 5/4 of a wavelength, right? Or the wavelength equals 4L over 5. It plays the 5th harmonic. 4L over 5. So this is the 5th harmonic. N equals 5. And that's the way it goes. It only plays odd harmonics. It sounds a little different. Okay? Now, I'm going to pass this around the room. And we'll run out of time today probably. But you're to put this up against your ear and extend it out like this. And as I talk or you hear sounds, depending on the length of this, you'll hear certain of my sound waves resonate louder than others. And certain sounds that I speak will become louder and certain ones won't. Because you're going to have it at just the right length that it resonates the frequency that I'm speaking. All right? So, yeah, you got to look stupid. Put it up against your head. All right.
And you have to have your hair off.
Yes. Hey, let's look at your e-homework, because I think I've covered everything in your e-homework. Let's take a look. Okay, look at question number 1, 2, and 3. You have a little vibrator thing there for this wave. If the vibrator thing vibrates, like on mine, at 188 hertz, then what's the frequency of the wave? 188 hertz. If they tell you that the length of the string is 5.1 meters, and I have 1, 2, 3, 4, 5 antinodes, so mine looks like this. 1, 2, 3, 4, 5. This is oscillating up and down at 188 hertz. So my frequency is 188 hertz. This is 5.1 meters. What's my wavelength? I've got 1, 2.5 waves, right? So I take 5.1, divide by 2.5, oops, 2.5, what the heck? 2.5, and that gives me a wavelength of a little over 2. So I know my wavelength, I know my frequency, I can now find the velocity in the wave, right? Piece of cake. It asks you several things, but one of them is, question number 2, how many complete loops, or antinodes, would you find if you change the mass? Now that goes back to our equation. Velocity equals, what is it? It's tension over mass per unit length. Okay? How are you going to find your tension? Well, they got a mass hanging out over here, right? So it's just going to be equal to mg, right? So there's your tension. And this is the mass of the string.
Wait, but does that work? Because it's a mass at the end, not at the whole.
Yeah, but what they have is they have it over a little pulley, I think, and so
We'll assume it's.
we'll assume it equal to mg. What if you come up with that it's supposed to have 6.3 loops?
Then it won't form.
They won't form.
Frequency.
And it tells you if it won't form, put in an answer of -100. That's the mass of the string. Now, they may give you the mass per unit length already. If they give you the mass per unit length already, just plug it in for M over L.
I don't know.